Hello. In the last lecture, I have explained the basic ideas of hypothesis testing. So we started from the like how we can understand hypothesis testing in a model, like in the model approach. So without considering the data, what is we may understand the hypothesis as an assumption. So depending on whether you take the assumption or not, you can think of unrestricted model and restricted model. And then also I explained quadratic form, and it follows a chi-square distribution. And then I explained four different types of tests: Wild test, Hausman test, criterion-based test, and gradient test. So today, I'd like to uh, review those four types of tests using graphs. So I explain them just purely on the lecture note. But if I had a blackboard, then I would show you these graphs to explain them. So let me try that in PowerPoint. So first, we are going to consider a criterion function like this. So here in the graph, let's think about minimization. So this dimension is, so theta is one dimension in the x-axis. Horizontal axis is for theta, and for each value of theta, there is the criterion function q0. So q0 is a convex function which has the minimum at theta 0. So we would like to uh, estimate this, and we would like to see if this theta 0 satisfies a certain restriction or not. Let's think about this. So suppose that now we can think about the null hypothesis as another function of theta. Suppose that the null, can you see right now? You can see that. So the null hypothesis is given by r, restriction r, theta 0 equals to 0. So it's represented by a function. So think about two different cases. Blue, if the restriction, the hypothesis is given by blue, then the only point, the only theta that satisfies the blue restriction is this point, which is the restricted value of theta. And then this point is different from the minimum. The true parameter is here, but your restriction implies a point here at a different point. So this blue hypothesis is wrong. But if you think about red, suppose that the red is another hypothesis, another restriction, then this restriction, this is another function, and this function equals to 0 exactly at the true parameter. So this restriction is a true restriction. So restriction holds at the true parameter value. So the red hypothesis is a true null hypothesis. So this hypothesis is a good hypothesis, like true hypothesis. And then now let's think about this. So just simply replace the population criterion function and the population restriction function with their estimates. So estimation is usually straightforward. And then let's think about what happens if you have this hypothesis. The first approach is that, so this is this is the wild test. Wild test calculates unrestricted estimator first. So the unrestricted estimator is obtained by minimizing the criterion function. So minimize the criterion function, then you obtain theta hat, and then evaluate the restriction function at that point. The point is lambda r hat. which is different from 0 here. So if this is different from 0, then you have to reject the null hypothesis. So the restriction function is not 0 at this point. This is the first approach using wild test. And second test, like think about gradient test or Lagrangian test. Lagrangian? Anyhow, so then as I explained in the lecture note, we know that the true parameter, the unrestricted estimator, would have a 0 first order condition. So the first order condition at the unrestricted estimator is 0. But now you are imposing the restriction in this minimization problem. So you minimize the criterion function subject to this restriction function equals to 0. But the only point that satisfies the restriction is this point. So this is the minimum because you have no other choice. This is the only choice you can handle, you can choose from. So therefore the minimization of the criterion function given the restriction is this. At that point, the slope is non-zero. And if the criterion function is convex, and if the restricted estimator is different from further from the true unrestricted parameter, unrestricted estimator, then the slope will be steeper. It becomes steeper as the theta r goes away from the unrestricted estimator. So this slope is somehow, it captures, in some sense, captures how different these two are, or how different the minimum and the restriction is, right? This is the gradient test. And the third case, think about criterion-based test. Here is the unrestricted estimator. Here is the restricted estimator, right? Then it's clear that the minimum is obviously achieved at the unrestricted estimator. So this is the minimum. Minimum is achieved here, but subject to the constraint, subject to the restriction, the minimum is only at this point. Is at this point, which is much higher than this guy. So the restricted minimum is greater than the unrestricted minimum. So the difference is also so the difference captures how different the restriction is from the unrestricted minimum. That's another approach. So you are looking for the distance here. And finally, simply you can measure the distance between this point and this point by the Hausmann test. So, like as you can see, the idea is we would like to see the distance between the true minimum, the minimum of the criterion function, and the restriction, the point that satisfies the restriction. How far this is? There are 4 different ways. One is to measure this distance, this value, and second is to measure the slope, and the third is to measure the difference, and fourth we measure this distance. So that's 4 different approaches to handle the same null hypothesis. So, and as I explained in the last lecture, there are one test may be better or more easier to implement in some cases. So you better understand all 4 approaches, and then you can choose the best one from them. Okay, we are going to start the application. So we will apply this general framework to the instrumental variable and the classical linear regression models. So I will continue in the next video. See you later.